Let's next tackle a problem that's got some real meat to it. Let's say we have an insulating sphere, and again, as a reminder, when you have an insulator, it means that the charges on it stay where they are. Okay, so the charges are on the sphere, and those charges are not free to move around. So we might draw the charge something like this. Now this sphere is different from our review material because this has a volume charge density, charge over volume, that is not constant. So the density is some constant alpha times the distance from the center of the sphere. Okay, so that's different this time. The charge density is not constant. We're going to try and find the electric field as a function of distance from the center, both inside and outside of the sphere. Okay, so we're going to use Gauss's law, and we're going to apply Gauss's law with spherical symmetry. Gauss's law states that the net electric flux through any closed surface is the integral of E dot dA over the closed surface, and that's equal to the net charge enclosed by the surface divided by the constant epsilon naught. Let's deal with the integral part first. So since we have a sphere of charge, then we're dealing with spherical symmetry. So our sphere means that the electric field points out radially. So that's what our sphere looks like. If we're trying to find the electric field inside the sphere, so E of R less than R, when we draw our Gaussian surface, we pick a surface that matches our sphere. Our Gaussian surface will be a sphere. Since we want the field inside, we're going to make our Gaussian surface a sphere with a radius smaller than the radius of the big sphere, than the insulator. This symmetry is the same as if when we're trying to find the electric field outside our sphere. So if we're going to go outside, the electric field is still radially outwards. And if we want the electric field outside, then what we do is we draw a Gaussian surface that's a sphere, but this time it's bigger than our insulating sphere. This time that's our R. Okay, let's deal with the integral part first. The integral of E dot dA is equal to the integral of E times dA times the cosine of the angle between E and dA. We know that dA is a vector that sticks straight out of the surface, and our electric field comes out radially outwards. Those two vectors are parallel, so the angle between them is 0. Cosine of 0 is 1. Our electric field, if we're a constant distance from the center, then our electric field is a constant, which means it comes out front of our integral. So then we're left with the integral of dA times the cosine of 0, which is just 1. The integral of dA is A. A refers to the area of the Gaussian surface, or area of a sphere, which is 4 pi r squared. Okay, so no matter which one we're doing, we're going to use this as the result for the integral of E dot dA. Okay, the next term in our Gauss's law expression we're going to have to worry about is Q enclosed. So what does Q enclosed mean? It's the net amount of charge inside the Gaussian surface, or enclosed by the Gaussian surface. Okay, so for this one, if we're inside our sphere, it's going to be some fraction of the total charge. If we're outside the sphere, it's the total charge. If our charge density is constant, then this is not too difficult to figure out. You would find the amount of charge by doing the density times the volume. And that's what we did in our review video. You can go back and check that out if you're not really sure how that works. But when your density is variable, this becomes more complicated. And it's complicated because our density is variable. Okay, so right in the center, right here, the density is 0. As we go out, it gets bigger, 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 and your density is the biggest on the outside. So we're going to have to figure out how we're going to find that amount of charge. Go on to the next slide, and we'll start to get our idea for how we're going to find the charge. So let's think about this one first for inside the sphere. We're trying to find how much charge is inside that circle of little purple dotted lines. I'm going to draw it again, a little bit bigger because I want it to be nice and visible. So here's my insulating sphere. Here's my Gaussian surface. Let's get the idea first of what we're going to do. If I want to find the total amount of charge on this Gaussian surface, I could find the amount of charge in this little pink circle. So I could find the amount of charge there. Then I could find the amount of charge in that little pink ring. I could find the amount of charge in this next little ring, this next ring, this next ring, one more ring. And if I find the charge in each one of those little rings and add them up, then I'm going to end up with the total charge. Okay, so that's my idea. I know that the density depends on how far away we are. I'm going to find the charge using the density in each one of these little rings. I'm going to add them all up. That's going to give me my little charge. So what I've just said there, why don't we even write that down just to make sure we're good. So I'm going to add up. Remember, the way we add things up when we have a bunch of small things means I'm going to take an integral. I'm going to add up the charge on each little ring. Now, a ring is a two-dimensional construct. We have a three-dimensional construct, so that little ring is actually a shell. So it's not just a ring, but it's an actual shell. On each little ring, so that would be 2D on each little shell. That amount of charge is going to be dq, and we'll get the total charge inside the Gaussian surface. That total charge is Q enclosed. Let's write that down as a math equation. Q enclosed is the integral of each little dq. The limits of this integral somehow are going to be from the center out to the radius of the Gaussian surface. Okay, hopefully we're good with that idea, that concept of how we're going to construct this. So that's my little r, radius of the Gaussian surface. This is the radius of my whole insulating sphere. So what is dq? That's a good next question. So dq is the amount of charge on each little shell. dq, the amount of charge, is the density times the volume. And the volume of each little shell we'll call dv. So d because it's a little bit, v for volume. So dv equals volume of one little shell. Okay, how are we going to identify the shell? Let's shade one in on the picture. I'll just pick one at random, because normally we do shade in a dq when we start our problems. Okay, so I need some ways to identify it. I want to write down the radius of this little ring. I've already used little r, I've already used big R. I'm going to call this radius r primed. So with radius r primed. If you don't like the primed notation, I suppose you could call it something else, s or z or k or something. It also has a thickness. And the thickness is a little bit in that r prime direction. We'll call that dr primed. How are we going to find volume? Well, we know that volume is area times thickness. So the area of that little shell is 4 pi times r primed squared times the thickness dr primed. Okay, this is going in for dv, then dq is going in right here, then we're going to do our integral and we're going to have our net charge. Hopefully you're still with me on the process. So my Q enclosed, I think I'll move to a different color. Oh, I'll go back to black because that's what we were working on for Q enclosed. So Q enclosed equals the integral of dq, which is the integral of rho times dv. Let's put in what those things are equal to. Remember, rho is our charge density. It's a variable, and it's a constant alpha times our distance from the center. So it's the integral of alpha. Our distance from the center now in our r primed notation is r primed. dv is 4 pi r primed squared dr primed. This is definitely something we know how to take care of. Okay, let's take our constants out front. Alpha, 4, and pi are constants. Then we've got the integral of r primed times r squared. That's r primed cubed times dr primed. I'm guessing this is an integral most people are familiar with. And let's remember the limits of our integral. We're starting at the center where r primed equals 0. And we're stopping at our Gaussian surface because we're trying to find the charge on the Gaussian surface. So we're stopping at r, the radius of the Gaussian surface that we used in this notation right here. Okay, so the integral of r cubed is r to the 4 over 4. So that's alpha times 4 pi times r prime to the 4 over 4, evaluated at r and 0. I'm going to cancel those 4's out straight away. Alpha times pi outside of r to the 4 minus 0 to the 4 equals alpha times pi times r to the 4. Okay, that's how much charge is inside our Gaussian surface. Now we can put together our terms. This is what the integral part is equal to. This is what the Q enclosed is equal to. Let's put it together with Gauss's law and we'll find the electric field. So remember, we're going inside the sphere. We'll write Gauss's law. Let's fill in our Q enclosed, which is alpha times r to the 4. Alpha times pi times r to the 4. Don't want to forget that pi, divided by epsilon naught. Let's see, so then our E is equal to alpha. The pi's cancel. R to the 4 over r squared leaves us with r squared. This 4 comes down in the denominator. And we've got our epsilon naught. Electric field is a vector, of course, and it points radially outward. You could also put in the r hat unit vector notation if you wish. Okay, that's the expression for the electric field when we're inside the Gaussian surface. When we're inside the insulating shell. Next, let's do when we're outside the insulating shell, the insulating sphere. So what happens when we're outside the whole thing? So here's our total sphere. This time our Gaussian surface is out here. I'll just put outside because that one is inside. So that's little r, this is big R. So now what we're trying to find is what is the net charge enclosed by the Gaussian surface. So Q enclosed is the net amount of charge inside this purple dotted line. That's going to be however much charge is on the insulator. Okay, there's no charge in this white space here, that's just empty. All the charge is on our insulating sphere, so we're going to have to add that up. We're going to go back to the same process, except now we have different limits. We can put all of our rings here again. This time when we do our integral though, we won't stop until we get to the very edge. So exactly the same process. Let me get my pink pen and we'll draw all of our shells. So we'll start at the center. We'll take shells all the way out. Okay, that's maybe the best I can do with those shells there. And if you want to see it just one more time, we're going to pick one of these little shells to be the DQ that we're talking about that has volume dV. It's got a radius r primed. It's got a thickness dr primed. Okay, I won't write out all the notes again this time because the notes are exactly the same as last time. So my Q enclosed is my net charge on my insulator. It's the integral or the sum of the charge on every one of those little shells. I find the charge on any one shell by doing density times volume. A little bit of volume because each shell is small. The density is the constant times how far we are from the center. dV is a little bit of volume, that's equal to the area of the shell times its thickness. Take the constants out front. So same integral as before. This time we start at r primed equals 0 and we finish out at the surface of this shell because we're trying to get the charge on the entire insulating sphere, so we go right out to the radius of the entire sphere. So that's equal to alpha times 4 pi times r prime to the 4 over 4, evaluated at the radius and 0. Those 4's can just cancel for us. Alpha times pi times r to the 4, subtract 0 to the 4, equals alpha times pi times r to the 4. Okay, so this time our net charge is a constant, and it's the same form as we had before, except now our radius is all the way out to the surface of the sphere. Let's apply our Gauss's law. Integral of E dot dA equals Q enclosed over epsilon naught. We already showed that the integral of E dot dA is E times 4 pi times r squared equals Q enclosed, which is alpha times pi times r to the 4 over epsilon naught. We'll solve for our electric field. That's alpha times r to the 4th. We see our pi's cancel. Then we divide by 4 epsilon naught times r squared. To write your field as a vector, we remember that it points outwards. Okay, so there's the electric field due to that insulating sphere with a variable charge density. Of course, it could be pretty interesting to draw a graph of that electric field, mostly because physicists tend to graph everything. So if we were going to graph everything, why don't we just write down those two equations? So if r is less than r, our electric field, alpha r squared over 4 epsilon naught. If r is outside, E is equal to alpha r to the 4 over 4 epsilon naught r squared. You might notice that r equals r. Both equations give the same value of alpha r squared over 4 epsilon naught. So it's good that they're the same value no matter which side you approach it from. If we were to do a graph, we would put our distance from the center on the horizontal, our electric field at the vertical. The interesting spot would be at r equals r. So if we're inside the sphere, our electric field is proportional to r squared. So it goes up as a curve, something like this, till it hits some constant value. So this is E proportional to r squared. And then once we're outside, it falls off as 1 over r squared. And then right here, the maximum value is alpha r squared over 4 epsilon naught. Okay, so that's a pretty good look at the electric field of an insulating sphere with a variable charge density.